First, I'd like to thank the organizers for the warm invitation for this very nice conference. It's really opening my eyes to know more about aging. So that also implies that I'm not an expert in aging, but I know more about complex networks, in particular, percolation theory aspect of complex networks. I guess the most knowledge I know about related to aging is more about aging in spin glass systems, which is a pure physical concepts. But let's put that aside. So I'll talk a little bit more about percolation theory in complex networks, a good continuation from Yiho's previous talk. So you already know the basics of complex networks, so I can go a little bit in depth. And then later I'll try to relate it a bit more to some examples, use some examples to illustrate what are the peculiar phenomenon in the percolation phenomenon in complex networks, then followed by some examples in social networks to illustrate the concepts, then ends with some latest research, not by myself, but in the field. How do they apply percolation theory in aging, especially in terms of neural networks, like biological neural networks. So yeah, I'm falling from IHPC A-star and also Department of Physics and US. So as you see, this network is actually a very typical phenomenon of percolation, which is also actually a spreading phenomenon. So it's some kind of something spreads from the bottom, then it spreads out all the way to the whole network. So this gives you a rough pictorial notion what percolation over a network is. Yeah, essentially it's something percolate from one side of the network to the far end of the other sides. So, so usually there are two typical definitions of percolations. One is called link percolation, the other is called node percolation. So the definition is a system transitions from a disconnected or connected phase. It's not the exact most rigorous definition, but it's some sort of very layman definition that is easy to understand and generalizable to different kind of systems. In this case, it's particularly this 2D lattice. They're the same lattice. So in terms of link percolation, essentially it means you randomly occupy the links in the network. Yeah, so you can see the orange links occupied, then the connected links. So they form clusters of connected links and nodes in the network. So you can usually label the largest connected component or largest connected cluster as orange nodes. In this case, it moves around as the network, the number of links that is being occupied increases. So then eventually you can see the cluster grows. At a certain point in time, the connected cluster connects to opposite ends of the network. So then we label them as purple cluster. So at that point, we call it percolation happens, right? So analogously, you have a node percolation. So instead of occupying the links, you can occupy the nodes. So in that case, you also form like a large connected clusters. So when the connected cluster connects opposite ends of the lattice, we say a percolation happens. So as you can imagine, this was first studied in relation to materials, right? If you think about a crystal, if you want to break a crystal, as you apply more forces to it, there's more and more broken bonds in the crystal. At a certain time, when there is enough fraction of bonds broke, then the whole crystal will fracture, right? So that's why we call it the percolation happens. You can also say percolation is kind of like fluid pouring through one side of the lattice and it percolates through the other side. So yeah, I think I've spent enough time to mention what is percolation. So of course, we're talking about complex networks. It's not a 2D lattice, it's complex. So usually on complex networks, we have a similar definition. So it's also when you just say, in this case, it's a link percolation. You just randomly occupy the links on the network. At a certain time, when you occupy enough links, can see the connected components gets larger and larger, and suddenly a very large component of the purple component emerges. And that's why we call the percolation happens. So there's a strict mathematical definition for it. So the connected component needs to be infinite in size. Why is it infinite? There's another underlying assumption is the whole network, the embedded network, the whole size of the network is infinite in size. Then the subset that is connected also needs to be infinite in size. Then we call it the percolation happened. So there's a strict definition, but usually, of course, real systems are always finite. You never encounter an infinite system. So there are some ways to identify where the percolation happens. I think the previous speaker mentioned something about it. I think the last talk in the morning session also gave some flavor about it. I'll just illustrate a simple illustration here as well. So usually, so the horizontal axis you can see is a chance to occupy a link or the chance to spread something across a link. It can be spreading a damage of a link or spread information or even a virus. So then the vertical axis is the size of the largest connected component, which is essentially the size of the purple cluster. So you can see before a certain threshold, the purple cluster size was 0, but at a certain time, suddenly the purple cluster becomes non-zero and peaks out at 1, which means it covers the whole network. So at this point, we call it the percolation happened. So why percolation is important? Because it's actually generalizable to a lot of phenomena, real-life phenomena. So when we talk about node percolation, usually we associate it with network resilience, which Iho just mentioned. So you can see if it's a brain network, the nodes of the network are neurons. So giant cluster, it just means like whether a large portion of your brain neurons are connected to maintain some kind of coherence. So resilience problem is maybe, I mean, as the non-biologist or neuroscientist interpretation is probably a loss of neurons, then resulting into degradation of brain function. But the clear definition here, the degradation is in addition to just shrinking of the largest connected components, it's also actually the phase transition associated with the loss of the giant component, which means your brain is no longer a connected, coherent whole to process information. Of course, there are other examples on internet, flight network, ecological network, and human contact network for like vaccination of COVID and stuff like that. So that's why percolation phenomenon has been important in all these studies. So of course, you can also talk about link percolation. In this case, in brain, it probably means the synapses get damaged rather than the neurons. Then maybe resulting in degradation of brain functions as well. So yeah, I think I go a little bit faster. So I just illustrate through something I'm more familiar with about percolation, that is about spreading phenomenon percolation, to illustrate some of the key properties of percolation. So you can actually mathematically link a spreading of something on networks to a percolation phenomenon as a link percolation phenomenon. So if essentially is something, if information or virus spread from I to J, then we say this link from I to J is occupied. So when we are saying that, what does it mean it percolates? So if it percolates, it means that thing becomes a global phenomenon. The virus or the information spreads globally to a lot of people. And otherwise, it only is a local outbreak. So the whole network is disfragmented. So of course, if you look at neuroscience, probably you want a brain to work in this phase rather than this phase, right? But that's a simple picture of phase transition. But actually, percolation phase transition can be more complex than the picture just now. So in usual cases, depending on the network structures and the way you define the mechanism, things can, the phase transition can exhibit as first order, which is an abrupt jump. Oh, thanks. Yeah. And the second order phase transition, which is a continuous transition. And also it depends on the structure of the network, whether there's hierarchical structure or the detailed spreading mechanism of the network. You can have very complicated phase diagrams, like of different kinds of phase transitions, depending on all these factors. So it really depends on the problem at hand. You can manifest itself in all one of these different contexts. So there's a famous paper about the interdependent networks where in I guess, which year was that? 2010, yes, 15 years from now. So the first one to discover the abrupt phase transition in percolation phenomenon. So that's the case where you have two interdependent networks that operate upon each other. Then you can have very catastrophic percolation behavior where suddenly the whole system, it looks like at this point more than 60% are connected, but suddenly the whole network fragmented and lost its function. So then you can really use this, some of the percolation. So there's another intriguing property about percolation is, I need to go a little bit faster, so is about the bimodal distribution. This is a mathematical property that you can really rigorously prove it, as well as simulate it. So when percolation happens, you can plot the distribution of the connected components in the network. So the horizontal axis is the fractional size of how big is the individual components, and the vertical axis is just the frequency. So you can see there's a clear bimodal distribution when after percolation happens. So on the right, you have a very sizable connected component, what we usually call the giant component, which is really huge. You see, it's like about 10% of the whole network. But other than that, all the other components are extremely small. And actually, they have a very clear exponential decay in terms of the distributions. So as you can see, you can also see from this simulation result on a real network. You can see that actually from the same red node, which is a seed node that the spreading started from, you can either have very, very large outbreaks, or you can have very small handful of nodes that are being affected. So that corresponds to the bimodal distribution, and this can be leveraged. Actually, we have leverage on this to identify the important nodes in say, in this case, it's a social network. But why I'm giving these examples is because a lot of people has also been using inferential nodes identification algorithms to try to understand what, in biological networks, what are the inferential nodes, so they can gain some knowledge about the biological network's function itself. So, so I'm giving this illustration to show that actually there's a whole lot of different measurements of node properties in networks, like a degree centrality, K-shell, betweenness, closeness, eigenvector centralities. But actually, if you do leverage on the very neat and nice mathematical properties of percolation, you can actually create some kind of percolation-based algorithm that that is high-performing and also, computationally extremely efficient. So then, I just spend a few minutes to relate to aging. Though this, from here onwards, is not really my work, but it's what I learned from the recent years, some of the, a few papers that relates percolation to aging. So one is to understand the brain functionality. So as I mentioned before, so is this paper by these authors. So they talk about percolation analysis to understand network connectedness. As I mentioned before, percolation essentially tells you it's a transition from the network being fragmented to being connected. So if you define the brain function as functions properly as in the state where it is really globally connected, then that's in the percolator transition, right? So what they do is they look at the full flight connectons, neural networks. So they just tune the excitation inhibition ratio to see at what critical threshold then the connected emerges. Then they went on and forth to study some of the efficiency and robustness of the brain functions in terms of the percolation framework. So there's something I would like to stress here is another complication comes here is because they do introduce directions in these networks. So the giant connected component is no longer as simple as the undirected network. So the more proper form is, name is called the giant strongly connected component, which means because of the directions of the network, because you can go from node A to node B, but not necessarily vice versa. So this is a strict definition. So this GSCC is a strict definition of the giant component, which defines the largest connected component of the brain. So when it changes from 0 to non-zero, that's where they say the brain gains some functions. Then they came up with some optimal ratio between this excitation or inhibition. They say it's around like 0.5. That's where it saturates. But the percolation transition happens when it's 0.3. So, and another interesting study is this study. So I guess it's closer to aging. So it's about Alzheimer's disease. So they do compare, they do look at the mice, fMRI data. And they do like they construct a network, then they do percolation perturbations, which means they remove nodes from the network one by one, depending on different measurements of the node, being like different centrality measures, which means how important or influential they are in the network. If you remove them one by one, what they find is that actually the control group, which are the healthy group, are more robust against this kind of node removals in the network, where in terms of the Alzheimer's disease patients, they are more fragile. So this is kind of provides some potential for a biomarker for how you identify brain degeneration diseases in terms of in the percolation framework. With that, I'll just give my 2 cents. Again, I'm not really an expert in aging, but I just try to provide some of my perspective on percolation theory and how it potentially can help. So percolation analysis is really like a systemic resilience measurement. So it's a phase transition, so it has all the nice properties of phase transition in physics, but it also has very diverse phenomena in terms of how it shows up in different type of systems. In particular, related to aging, so as far as I can see, the work is limited, but the flip side means maybe it has good potential to be used in aging research. So one potential is percolation framework help you to identify which are the key nodes in biological networks, so you can learn more about their functions. And the other is maybe as a systemic biomarker in neurodegeneration, which are usually associated with aging. So yeah, so with that, I would like to thank you for your time.
So let me ask the question.
Okay.
So your percolation network there seems to be like a random network or regular network?
I mean, the example here?
Yeah.
It's a random network.
So we just learned that biological networks, for example, are scale-free.
Yeah.
Right? So if you have a certain number of hubs, if you add there, how will different your results will be if you consider that?
Yeah, so if it's scale-free, then actually your percolation threshold will be very close to 0. Right. So that's the first thing you learn. So then, also if you are scale-free, when you do attacks, like what they do here, in this work, essentially they are attacking the network, but they are not randomly attack the network. So if you start by attacking the hubs, it becomes more fragile. But if you do random attack on the scale-free network, it's actually more robust against those random attacks. Yeah.
Thank you.
Yes, thank you. Great talk. Really love this stuff regarding complex systems and percolations. I have a quite maybe naive question from your point of view. When we speak about percolation, we consider nodes which are countable, discrete nodes in a countable space. Was there any generalization of percolation theory to Hilbert space where nodes are actually uncountable? And yes, this one.
I mean, it's a good question, but I'm afraid it's not something I'm very familiar with. Yeah. But maybe something worth looking out for. Yeah.
Thank you.
Yeah, 2 quick questions. So the first is that if I understand this sort of formalism correctly, it's not the kind of this sort of a thermodynamic kind of phase transition, right? Where you have to think about temperature and conserve system, because this, in other words, is it strictly speaking depend on the boundary size, or in this case you don't care about that at all? Because in biology, there's always some finite size effect. So.
Yeah, actually here we don't really have a boundary. I mean, the theoretical framework doesn't really have the boundary effect. Yeah, you're right.
Okay.
Yeah, but it has actually, in the first question, in the earlier question, the early part of your question about the thermodynamics, actually the percolation theory in networks, the mathematics has deep connection with thermodynamics and the phase transition in statistical mechanics. And even there's a bunch of scaling relations and scaling laws, critical exponent. They are actually closely associated with just the traditional thermodynamics knowledge. Yeah.
And the second question is, maybe you talk about it, but I might have missed it. But do you have, because in biology, for example, these nodes could also be actively, popping up or vanish. And so I was wondering whether there's been work in this sort of formalism to see whether there's new behavior that emerges.
So you mean like a growth and death, right?
Yes.
Yeah. There has been studies. So then it's no longer, I mean, of course, the system prescription is somewhat different from this, but there has been other studies looking at this as well. Yeah.
Okay, catch up with you
Okay,
later.
in the interest of time, thank you, Professor Feng Ling, a wonderful talk.